Hello and everyone, welcome to Deeksha Karnataka YouTube channel, and in the Masterstroke series today I am going to discuss another important chapter, moving charges and magnetism. This is a very high weighted chapter for your PU2 as well as your KCET exam. Now if you are wondering that if you need the PDF of this lecture, then don't worry, you can download the PDF of this lecture and all our lectures, but that will be exclusively available in our WhatsApp channel, and the link of the WhatsApp channel given in the description section of this video. And if you have not yet subscribed to our channel, what are you waiting for? You have to subscribe it now, and we are going to discuss all the important concepts for your PUC as well as KCET. So don't go anywhere, wait till the end, and you will be benefited from this preparation, because within at least 1 hour we will cover a very important high weighted chapter with in-depth discussion. So let's start. First we will see what are all the concepts that we are going to discuss today. We will start with Lorentz force, then we will discuss about force on a current carrying conductor. We will also discuss motion of a charge in magnetic field. We will also discuss Biot-savart law, Ampere's law, and solenoid. Last but not the least, galvanometer and their conversion between ammeter and voltmeter. Okay, so let's start with Lorentz force first. Okay, not Lorentz force first. Let's start with an introduction. So what is this introduction? Moving charges or currents produce a magnetic field in the surrounding space. So we know that this part we have learned in our class 10th, the magnetic effect of electric current. So if there was a current carrying wire, and if we place a cardboard around the wire, okay, we have observed some circular rings forming on this cardboard, right? We have done some iron filing on top of it. We tap it and we realize there is a circular ring around it. That means why it is so? Because iron being a magnetic material, they are forming along the loop, along the magnetic field lines present in the region, and that's why they are forming concentric circles. Okay, so magnetic moving charges produces current which is in circular in nature. SI unit of magnetic field is Tesla. This is the first time we are introduced to magnetic field. Magnets are there, but in this particular chapter we will not discuss directly about magnets. We will discuss about magnets in our next chapter, but in this chapter we will mainly discuss about how magnetic field is produced because of the motion of charges or motion of current. Okay, so SI unit of magnetic field is Tesla. The dimension of it is m to the power -2 a to the power of -1. Okay, there is no L involved. Okay, and if you see that here we have shown some current, which is, first of all, this current is coming out of the page, this current is going into the page, and magnetic field due to this one and this one are in the reverse order. Okay, so this is a magnetic needle. If you place a magnetic needle around a current carrying wire and if you rotate it, you will eventually find a circular pattern. Okay, now let's move on to Lorentz force. So when a charge moves through a space having both magnetic and electric field, it experiences a force. Okay, so we know that if there is an electric field present, okay, and if we put a charge over here, then this charge experiences a force in the direction of electric field if the charge is positive, and in the opposite direction if the charge is negative. We have repeatedly studied this concept. Now this is a static charge, so this static charge will experience as a force in the electric field. Now if the charge is in motion, already in motion, and if you have some magnetic field present as well, okay, then this charge will not only experience electric field, but it will also experience magnetic field. It will experience not only electric force, it will also experience magnetic force. Okay, both forces will be acting on this charge. Now this will only possible when the charge is in motion. The electric force is given by Q into E, our old friend from the electric charges and field, and something new that we are adding, that is called force due to a magnetic field, which is dependent on its velocity, its charge and magnetic field. It is Q into V cross B, and if you combine these two forces, you get the total force acting on this charge, which is given by F equals to Q is common, E plus V cross B. Now remember that in this case you cannot simply add them scalar function wise, because they are vector quantities. You have to use vector addition method in case you find some problem. Now if you see some problem, that will be based on unit vectors, so you have to add them unit vector wise. Okay, you don't need to draw the physical vectors and add them. Unit vectors will be given I, j, k cap, and based on that you might need to solve one or two problem. Okay, so this force is called Lorentz force, very, very important. Now for most numericals we will use only the magnetic force in terms of scalar form, which is QVB sine theta. So as you can see here, we have a cross product. Okay, so if you remember any two vectors, say A vector and B vector, if we cross them, okay, and if we take the magnitude, we get AB sine theta. For dot product it was cos theta, for cross product it was sine theta. Okay, we understood, we may have understood, we may not have understood why it is so. Right now it is not time for me to explain why it is sine or why it is cos, but you should remember that cross means sine and dot means cos. Okay, if you remember that, then it will be very, very helpful for you to solve questions. So here this magnitude of this magnetic force is given by QVB sine theta. Now let's see one question. A strong magnetic field is applied on a stationary electron. Then the electron will move in the direction of the field, moves in an opposite direction of the field, remains stationary, starts spinning. So we have learned that the force, magnetic force acting on a charge is given by QVB sine theta. Now if the charge is stationary, that means the velocity of the charge is 0. So if you multiply with 0, then what you get? It will be 0. Okay, so even some number multiplied with 0 will still remain 0, so it will remain stationary. The charge will remain stationary. So if you are someone who is wondering that I will study tomorrow, because you are stationary, the force acting on you will still be stationary and your progress will be 0. So don't think that I will start tomorrow. Start today, start now. Okay, then you only be able to progress towards a better future. Now for that, to bring you to take you towards the better future, we have our ABHYAS KCET 2026 test series, where you are going to get 35 KCET tests. KCET level test means here the questions are exactly like KCET level. Okay, so they are not PYQs, they are the questions which are typically on the level of KCET. The questions that we are going to give you may not exactly come in the form of exact questions, will not come in your KCET exam, but the questions that we are going to give you, the concept that you are using to solve those questions, they will be 100% be coming in your KCET exam. So if you practice this 35 tests, then you will be always one step ahead of all of the competition towards your dream rank of getting a rank below 1000. And here you are not only going to get 35 KCET tests, you are also going to get KCET chapter wise KCET PYQs as a form of quiz, which is absolutely free. You can test your knowledge. You may have a book, you may have solved them, but whether you are able to solve them in a time limited format or not, that is very, very important for you to test. Okay, so it will come in a form of a quiz where you have to solve the questions and answer the correct one, and once it is done, it will give you the answer. Okay, this is the correct answer, this is the wrong answer. So everything will be provided to you. You have to check it out whether you are able to solve them or not. It's absolutely free of cost. without any extra cost. The price is 1499. Now if you are thinking that sir, you have increased the cost and saying extra cost, the same price we have launched in the last year as well, and we are going to give you the same price for this year with additional KCET PYQs this year. Okay, and if you are wondering that I may be not able to purchase it, you can try our 4 free tests which is available by registering yourself in our registration link given in the description of this video. And once you register, you can use our app or website and access those 4 free question papers. Right, it will not be emailed to you. By the way, some students are thinking that they will register and they will get the 4 free papers on their mail. No, it will not come to your mail, not come to your WhatsApp. It will be accessible only through our website, so that you are familiar, we get yourself familiar, okay, whether it is good or not, and based on that you can make a wise decision. Now let's continue with our discussion. So force on a negative charge is opposite to that of a positive charge. Suppose we have a positive charge and we have a negative charge, okay, and if you apply some magnetic field, or okay, if the force on this in this direction, then on this will be exactly in the opposite direction, so that the angle between them is 180 degree. Force on a positive charge will be exactly opposite to that of the negative charge. Now remember, in case of magnetic field, the direction of force is not as simple as electric field. Okay, in electric field it will be either in the direction of electric field or in the opposite direction of electric field. Whether in case of magnetic field, because it's a cross product and it depends on the velocity, so you have to find the direction of the motion. Okay, I will explain how to find the direction of the motion as well. Anyway, the vector product makes the force due to magnetic field vanish or become zero if velocity of the magnetic field are parallel or anti-parallel to the magnetic field. So if suppose velocity is in this direction, magnetic field is also in the same direction, then the force will be zero. Okay, or velocity is in the opposite direction as well. So in all these 3 cases, force will be zero. Magnetic force will be zero. Because parallel and anti-parallel means sine theta is 0 or 180 degree. Sine 0 is 0. Sine 180 is 0. So if the velocity and magnetic field, they are parallel or anti-parallel based on their direction, then it will not face any magnetic force. For example, if they say that electron is moving in the same direction of magnetic field, what will be the force on it? It will be 0. Because they are moving in the same direction means they are parallel. If they say that magnetic field is in the eastward direction, electron is moving in the westward direction, what is the direction of force? So that force will also be 0, because east and west are exactly anti-parallel. So anti-parallel means again the force will be 0. The magnetic force is 0 if charge is not moving, that is V is 0. So we have solved one question. If V is 0 also, the force is 0. So if charge is static, force will be 0. Now let's see one more thing, where motion of a charge in a magnetic field. Now we have a charge particle and it is moving in a magnetic field. So charge particle moving in a magnetic field. Now here we have a negative charge. If in case of positive charge, the direction will be opposite, that's why. Anyway, let's consider this negative charge, and the magnetic field is into the page of the paper. Cross means into the page of the paper, dot means out of the paper. So suppose a magnetic field which is acting into the page of the paper, a negative charge is moving perpendicular to the magnetic field, then something interesting will happen. The charge will rotate in a circular motion. The charge will rotate in a circular motion. It will not be able to escape the magnetic field. It will keep on rotating in a circular motion. This motion is called cyclotron motion. Okay, this motion is called cyclotron motion. Now there in the past there was a mechanism where a device was there which is called cyclotron, and you have to learn a little bit more about cyclotron, but that is no longer part of the syllabus, so you don't need to study about cyclotron. Okay, but what is important is that the formula and calculation, everything is part of the syllabus. Just the term cyclotron and a device called cyclotron is not part of the syllabus. Okay, now this motion, why it will rotate in the circular motion? Because if you try to find the direction of the force, the direction of the force will be in this direction. Okay, so when the charge is moving in this direction, okay, force will be in this direction. So basically it's a negative charge. So how to find the direction, by the way? Suppose this is the magnetic field. Suppose this is the magnetic field. This is the velocity. Then how can you find the direction of the force? Okay, the magnetic force. Direction of the magnetic force can be calculated using the cross product, where you point your fingers in the direction of the first vector, because it is a V cross B, right? V cross B. So V, first you have to point your fingers in the direction of V. Okay, then you curl your fingers towards the second vector, that is B. So V cross B, then your thumb will point in the direction of the force, assuming the charge is positive. In case of negative, if you use the same thing, negative charge means it will be opposite. That's it. Okay, because by fundamental principle, if the force on a positive charge is in this direction, force on a negative charge will be opposite direction. Okay, don't confuse yourself with positive and negative right now, but just remember, for positive charge you just simply use V cross B and your thumb will give you the direction of the force. That is the way to calculate the direction of force. So here in the force will be out of the page of the paper, so it will be a dot. Okay, three-dimensional, so it will be out of the direction of paper, or you can draw it like this. This will be the direction of force. Okay, it will be out of the page of the paper. Now, a charge moving in a uniform magnetic field will experience as a force F is equal to QVB. Now, if the sine theta, if they are perpendicular like this, here they are perpendicular, sine theta will be 1, so sine theta will not play any part over here. So, a charge moving in a uniform magnetic field will experience as a force F is equal to QVB, and that force can be calculated using another force, which is called a centripetal force. This force acts as centripetal force and produces a circular motion perpendicular to the magnetic field. So it is perpendicular to both velocity and magnetic field. Okay, so that force is called centripetal force. Why it is important? Because if there is a centripetal force, then the object moves in a circular motion. And in case of centripetal force, it has to be provided by an external force, and in this case that external force is this magnetic force. The magnetic force is providing required centripetal force, and based on that the charged particle is moving in a circular motion. The radius of the circular path here is given by R is equal to mv by qb. R equals to mv by qb. Angular frequency omega is qb by m. The time taken for one revolution is time period, which is also called cyclotron time period, which is given by 2 pi by omega. Angular frequency is omega, and you can even calculate the normal frequency, which is omega by 2 pi. So it will be qb by 2 pi m. Okay, these are all formulas which are important. Okay, angular frequency, time period, these are all important formulas that you should remember. Okay, so frequency is omega by 2 pi, angular frequency is omega, angular frequency or angular velocity you can say that is omega. Okay, so radius of the circular path is mb by qb, angular frequency is qb by m. Now let's move on. Now these are few derivations that might come in your PUC exam. So radius of the circular path is given by mv square by r, and that is equals to qvb. Qvb sin theta was there, but sin theta is 90 degrees. Theta is 90 degrees, so sin theta is 1. So this way you can calculate the radius of the circular motion. So this formula is also very, very important. R equals to mv by qb. And from here you can calculate the velocity as well. Velocity is qbr by m. Okay, if you know q, if you know magnetic field, if you want to rotate it in a particular radius, then you have to have this particular velocity. Now angular frequency can be calculated using V is equal to R omega. So if you substitute R omega over here, R will cancel and you get omega is equal to QB by M. Now if you see that omega is independent of velocity, omega does not depend on velocity. Time period is 2 pi by omega, that is 2 pi M by QB. Okay, so time period will be 2 pi M by QB. Okay, let's move on. One question: a proton, a deuteron and alpha particle having same kinetic energy are moving in circular trajectories in a constant magnetic field. If Rp, Rd and R alpha denote the respectively the radii of the trajectories of these particles, then which relation is correct? And this came in Comet K exam, not in KCET. KCET there was one question, proton and alpha particle. In Comet K they have added one more, that is deuteron into this. Okay, now how to solve this question? We know that radii is given by mv by qb. Okay, radius of motion is given by mv by qb. Now we have to calculate radius for individual particles. First is proton. So mass of a proton, say mp. Mass of proton is mp. Charge of a proton is only one positive electron. Charge of a positive electron. Okay, because it is only one positive charge, so it has to be positive electron. Equal to, equivalent to, right? So it is E. I am writing the charge as E. What about deuteron? Deuteron is a isotope of hydrogen. Okay, so it has mass twice that of a proton, because a deuteron has one proton, one neutron. Mass of a neutron is exactly equal to that of almost equal to that of a proton. So mass of deuteron is 2 mp. Charge is same as hydrogen or a single proton, that is E. Okay, so deuteron is basically, if you consider ionized deuteron, then its charge will be E. Okay, what about alpha particle? Alpha particle is doubly positive helium ion. Okay, alpha particle is doubly positive helium ion. So its mass is 4 mp, because helium has 2 protons and 2 neutrons. So its mass is 4 times that of proton, and its charge is twice of E. Okay, it has 2 protons, so it will be twice of E. Okay, now we will calculate these terms. So Rp is given by mp v by E into B. Now if you see that all of them have same kinetic energy. Okay, so all of them have same kinetic energy. That does not mean that velocity is same. Same kinetic energy means what? Kinetic energy is same, not velocity is same. If velocity is same, then it would have been a slightly easier problem. Kinetic energy is same. Okay, so kinetic energy, suppose kinetic energy is given by K, then we can say that kinetic energy is 2 into mass into velocity. Okay, no, let me use another formula, not this one. So if you see that mass into velocity, this will come for all of the particles. Okay, it will come for all of the particles. So you can say this is the potential energy, this is the potential momentum, not potential energy, what I am saying, momentum of proton divided by charge of proton and B. This is a shortcut way. Okay, this is a shortcut way. If you know the momentum of proton, you can calculate this in one step. So how to relate momentum and kinetic energy? So momentum of any particle is given by square root of 2m into kinetic energy. Momentum is given by 2m into kinetic energy, square root of. So momentum of proton will be, momentum of proton is square root of 2 mp into k. K is same, right? Momentum of alpha particle is 2 into 4 mp into k, and momentum of deuteron is 2 into 2 mp into k. Okay, these are the masses for individual things, and kinetic energy is same. Okay, so that's why this took a little bit longer. So Rp is given by square root of 2 mass of proton into kinetic energy. Kinetic energy is constant for everything. Magnetic field is constant, so E by B. What about deuteron? Deuteron, it will be same formula, 2 into 2 of Mp into K divided by twice of E divided by B. Okay, charge is also charge is same. Charge is same. So charge is same means this will be the formula. So from here you can say this is nothing but, if you take this 2 out, this will be root 2 into root 2 MPK by EB. Okay, so these two we have taken out. So we get radius of deuteron is root 2 times radius of proton. Okay, radius of deuteron is root 2 times radius of proton. Now calculate the last one, which is radius of alpha particle. So radius of alpha particle is given by 2 into 4 mass of proton into kinetic energy K divided by 2 into E into B. Okay, so why 4? Because mass of alpha particle is 4. So now you take this 4 out of the square root, you get 2 and divided by 2. So and you get 2 MPK by EB. Okay, so 2 MPK divided by EB. Now 2 MPK divided by EB is same as proton. 2 cancels and you get, this is exactly equals to radius of proton. So in this case, radius of alpha particle is exactly equals to that of proton. So radius of alpha and radius of proton are same, but both of them are less than that of deuteron. Both of them are less than that of deuteron. So correct answer is option 1. Okay, now let's move on. So this is a very tricky question. Comet K questions are usually very tricky, not that simple of Comet K. Now, not as simple as KCET. Motion of a charge in a magnetic field, but Comet K problems are very brain clearing problem. If velocity has a component along B, this component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B is before a circular one, therefore producing a helical motion. Let's see what is the meaning of all these complicated terms. Okay, suppose the velocity is not perpendicular to the magnetic field. So this is the direction of magnetic field. Magnetic field is in this direction. Okay, velocity is at an angle which is not perpendicular, some angle between 90 and 0. Okay, if it is a 0, it will move in the direction. If it is 90, it is move in a circle. But if the angle is between 0 and 90, in fact in more than 90 also possible. So if it is between 0 and 90, then what happens? Okay, so there will be a component of velocity along the direction of magnetic field, and there will be a direction of velocity perpendicular to the direction of magnetic field. Okay, the component which is in the direction of magnetic field, what will happen to it? It will move with the magnetic field, because this direction their force is 0. Force along the direction of magnetic field is 0, and this perpendicular component will make sure that it rotates in a circular motion. So this one will try to make it in the circular motion, this one will try to take it in the forward direction. Okay, and combining these two motion, what we will get? We will get a helical motion. This is like a spring. If you have seen a spring used inside your pen, then that is same as the spring. Okay, so both of the motion will happen simultaneously. So this one will try to take it in a circular motion, perpendicular. If normally if magnetic field and velocity are perpendicular, you see only circular motion. If they are parallel, you see only linear motion. Okay, so linear motion means velocity will not be affected by the magnetic field. But when you combine these two, very interestingly, then circular motion is also happening, linear motion is also happening, and combining circular and linear motion, the name of the motion is helical motion, and the shape is called helix. The shape is called helix. This shape is called helix. So with this help, that the charge is not only rotating in a circular motion, it is also rotating in a straight line line forward path. So it is rotated like this, it will move like this. Okay, now let's continue with Biot-savart's law. So Biot-savart's law is very fundamental law where you calculate the magnetic field due to any current carrying element. What is the meaning of element? Element means you take a small portion of a current carrying wire, okay, small portion of a current carrying wire, and due to that small portion, if you try to find the magnetic field at some point, then this is called a current carrying element. Okay, so the current carrying element is generally a vector quantity, and the direction of current element is in the direction of current. Okay, the direction of current element is in the direction of current. Okay, so if the current is flowing in this direction, the dl vector will also point in the same direction. Okay, now the magnetic field due to this small current element dl at this point P is directly proportional to the current that is flowing in the circuit. Okay, it is proportional to the length dl. Okay, so dB is proportional to I, dB is proportional to dl, the length. So bigger the length, more magnetic field. Now why we cannot take any arbitrarily bigger length? Because if there are not all the points are at the same distance, then only we can take the dl. Okay, if the for example, if you take dl over here, all the points only for a small distance, the dl will be same distance from P. Okay, it depends on which point you are taking and the dl you are taking. Now it is also inversely proportional to the square of the distance. It is also inversely proportional to the square of the distance, and it is also proportional to the sine theta. Okay, so dB, which is the magnetic field at this point, it depends on mainly four things: proportional to I, proportional to dl, proportional to 1 upon r square, and proportional to sine theta. Combining everything, we get mu naught by 4 pi is equal to I dl sine theta by r square. Okay, here mu naught by 4 pi is a constant, and mu naught is called permeability of free space, permeability of free space, and value of mu naught by 4 pi is equals to 10 to the power of minus 7 Tesla meter per ampere. Okay, so this is the unit of mu naught by 4 pi. Now force on a current carrying wire. So far we are discussing about single moving charges. Now we have slowly shifted into current. Biot-savart's law was the first. Now we have a current carrying wire, and we already calculated the magnetic field due to current carrying wire. Now if the same current carrying wire is now placed in a magnetic field, external magnetic field, what will happen? So magnetic field due to the wire and the external magnetic field, they will clash, and whenever there is a clash, there will be a force. Okay, so this wire will experience a force acting on it. So what is the value of that force? The force is given by BIL sine theta. The force acting on this wire is given by BIL sine theta. So this formula is important for numerical purposes. Okay, now magnetic field due to a straight conductor, derivation is not there. A magnetic field due to a straight conductor, if you try to find the magnetic field due to a straight current carrying conductor, okay, and wire is not infinite, this is a finite wire. This edge of the wire is making an angle, say theta 1, this edge is making an angle theta 2, then the magnetic field at this point P at a distance small r from the wire is given by mu naught I by 4 pi r sine theta 1 plus sine theta 2. This is for a finite wire, the angle will be given. Now instead of this angle, if this angle is given, suppose phi 1 and phi 2, okay, either you can convert into theta 1 because this is a right angle triangle, so this will be, suppose this is 30, this will be 60, okay, this is 60, this will be 30, so you can either convert it into theta 1, theta 2 and use this same formula, or if these two angles are given, you can use here cos theta 1 plus cos theta 2, cos phi 1 plus cos phi 2, okay, that formula is also you can apply. For a long infinite wire, the same formula is mu naught I by 2 pi r. Now this derivation is not part of the syllabus. You have to apply Biot-savart's law to find this formula. This formula you can use Ampere's law as well. You can, using Ampere's law, you can find this formula. Very easy. Now let's move on. circular current carrying loop. So we are trying to find the magnetic field due to a circular current carrying loop. The radius of the loop is given by capital R. The distance where we are trying to find magnetic field is given by x. Then how can we calculate the magnetic field? At this point P, to find the magnetic field due to point P, you have to take a small element dl over here. So direction of dl is in this direction, and these two are, both are tangent, so this will be 90 degree angle. So sine theta is 90 degree in this case. Sine theta is 90 degree. Only thing that you need to consider this internal angle, that is phi. Now the direction of the magnetic field will be in this direction. This is the direction of magnetic field. Now if you consider the direction of magnetic field, then this angle will also be phi, and you know that only the x component will be present, y component will be cancelling. Why? Because if you take a portion over here and another portion over here, okay, the magnetic field due to this will also be in this direction, so they will be cancelling each other. Okay, y components will cancel, only x components will present. This derivation is very, very important for all PUC students. Okay, and once you derive the relation, you will get B is equal to mu naught n I square by 2 x square plus r square to the power of 3 by 2. The derivation I have done in our Brahmastra series of the same chapter. You can go and check Brahmastra for moving charges and magnetism. Okay, capital N is the number of turns, total number of turns. Then the magnetic field at the center. Magnetic field at the center, okay, is given by mu naught ni by 2r. Okay, so where x is the x is equals to 0, and you can calculate the magnetic field mu naught ni by 2r. Okay, for a distance which is very, very far away compared to the radius. Okay, if the radius is small, distance is large, then this formula can be modified into this formula. Okay, the portion I have explained it over here. So B is equal to mu naught ni square r by 2x cube, because for x greater than r, you can take this small capital R to be 0. This is a larger number, this is a smaller number. So this portion you can ignore. Upper one you cannot ignore, by the way, because even if it is a smaller number, it is in the multiplication, you cannot ignore. If it is a plus or minus, you can ignore. Okay, so because you have ignored it, you can say that magnetic field is mu naught ni r square divided by 2x cube, and then if you multiply pi in the top and bottom and replace pi r square with the area of the loop, then this can be written as 2m by x cube. Okay, here m is NIA, magnetic dipole moment of the loop. So if you see that this formula, okay, this formula was same as electric field on the axis of a electric dipole, or axial electric field due to a dipole, which was 1 by 4 pi epsilon naught 2p by r cube. Right, this was the formula. Here also you get the almost same. Instead of r, we have written it using x. Okay, 2p is replaced by 2m. P was electric dipole moment, m is magnetic dipole moment. Okay, so this small current carrying loop is behaving as a small magnet. Okay, the current carrying loop is basically behaving as a small magnet. Now let's see one question. The magnetic field at the center of a circular coil of radius capital R carrying current I is 64 times the magnetic field at a distance x from the axis from the center of the coil. Then the value of x is. So first of all, we have a circular coil and the magnetic field at a distance which is, say, at a distance x. Radius is capital R. So magnetic field here, say, is B, then magnetic field at the center is 64B. Okay, so what is magnetic field B? B is given by mu naught, okay, I r square divided by 2 r square plus x square to the power 3 by 2. Okay, this is the formula due to magnetic field at a distance x. Now what is the magnetic field at the center? Magnetic field at the center is 64B, which is given by mu naught IR by 2. Okay, right, x equals to 0. sorry, mu naught I by 2r, mu naught I by 2r. So this is 64b. Now what you have to do, you just need to put mu naught by 2 I by r equals to 64 times this value, that is mu naught I r square divided by 2 r square plus x square to the power 3 by 2. Okay, mu naught by 2 cancels, I cancels. Now you need to do cross multiplication. So r square plus x square to the power 3 by 2 equals to 64 into r square into r, that is r cube. Okay, now if you see, there is a, first of all, there is a cube over here. So if you take the cube root on both sides, we get r square plus x square to the power half. Cube root means whole cube root, so this is gone, cube is gone, and 64's cube is 4. Okay, cube of 64 is 4. So 4r, cube root of r cube is r. Now what you have to do, there is a half to the power half, so you have to square both sides. You get r square plus x square equals to 16r, or x square equals to 15r square, or x equals to square root of 15r. Okay, this is a KCET question. It came in 2024. So don't think that all the KCET questions are easy. Mathematically easy, but you have to remember the formulas. If you remember the formulas, you can solve it. Mathematically it is not very difficult, so you have to improve your level slowly so that you can solve such questions. If you remember these questions answers, it will not help. You have to understand how it is solved. That is very, very essential to get a good rank in KCET. Now let's move on with Ampere's circuital law. The magnetic field around a closed loop depends only on the electric current passing through the loop. So here we have B dot dl is equal to mu naught I. Suppose we have a current carrying wire. One wire or more than one wire does not matter. If we consider a loop around the wire, okay, then it says this loop is C, this current is I, then the magnetic field at each and every point, say B, then B dot dl, dl is, suppose this is a dl vector, okay, this is B vector, then B dot dl along this curve C, okay, is equals to mu naught I. This is a symbol of close integration. Close integration means if you start from this point, you have to come back to this point only. This is called close integration. Now let's see one question. Two identical current carrying coaxial loops carry current I in an opposite sense. A simple Amperian loop passes through both of them once, calling the loop as C. Then what is the correct relation? B dot dl is equal to mu naught I. The value of B dot dl is independent of the sense of C. There may be a point on C where B and dl are perpendicular. V vanishes everywhere on C. So here we have two loops, basically say loop number A and loop number B. They are coaxial. Coaxial means they are having same axis. Okay, now suppose the current through this is I, current through this is I, but they are in the opposite direction. Okay, so if current is being carried here through the first loop, okay, if the current passing through the first loop is in this direction, then the current passing through the other loop in the opposite direction. Now you are considering an Amperian loop which is passing through them only once. Okay, so what is the net current? The net current is I minus I. So if you take this as positive, the other one will be negative, the net current will be 0. So once the net current is 0, then B dot dl should be mu naught into 0, so B should be 0. Okay, so because B dot dl is 0, okay, dl cannot be 0. Dl is a physical length, so dl cannot be 0, so only way it can be 0 is only B is 0. So B vanishes everywhere on C. B vanishes everywhere on C is the correct answer. Okay, don't fall for that. A very easy question, but students still make a lot of mistakes. Now, solenoid, magnetic field inside a solenoid is constant and it is given by B equals to mu naught Ni. Okay, B is equal to mu naught Ni. N is the number of turns per unit length. N is number of turns per unit length. So very important, it is the number of turns per unit length, not total number of turns. So magnetic field does not depend on how many turns are there, but it depends on the length, density of the turns. So more closely wound solenoid will have a more stronger magnetic field than having a same number of turns but in a spread throughout a length, okay, will have a smaller magnetic field. So magnetic field is basically dependent on how closely the wire is wound. Okay, solenoid is obviously, we have all seen solenoid, and if you are wondering where are they used, they are used in any form of speakers, okay, where you hear, maybe it's a speaker that you put in your ear or a loudspeaker which is producing loud sound during the DJ night. So everywhere the sound that is being produced have a solenoid installed inside it. Now, force between two parallel current carrying wires, this is also super important. Here we have two wires, one wire is carrying current in this direction, another wire is also carrying current in the this direction, or two wires, one is carrying current in the same this direction, another in the opposite direction. Okay, so what will be the force between these two wires? So force between any two wire having current, say IA, IB, and the distance between them is r, then the force between them is given by mu naught IA IB divided by 2 pi r into L, and the derivation is important for your PUC exam, and the derivation I have done in our Brahmastra series. Also from here you have can also define ampere, again that everything is done in our Brahmastra series. Now if suppose force due to, this is say our wire 1, this is say wire 2, if the force on this in this direction, say F1, then force on this will be in the opposite direction, okay, and this will be minus F1. Okay, so force on wire 1, both of the forces are equal but they are in the opposite direction. Why? Again our grandfather Newton, who says that every action has equal and opposite reaction. So if you consider one of them is as action, the other one will be as reaction. Okay, so F12 equals to minus F21. For force for unit length, force per unit length, which is the formula that you have to derive, length is equal to 1. Okay, length is equals to 1, and the force per unit length can be written as, force per unit length can be written as small f equals to mu naught IA IB by 2 pi r. You can remember 2 pi r or 2 pi d, whatever you are comfortable with. So this is the force per unit length. This derivation is important. Now remember one more thing, that if current are in the same direction, if the currents are in the same direction, they actually attract. Okay, if currents are in the opposite direction, they actually repel. Okay, they actually repel. So this force between these two will be, this one will be in this direction, this one will be in the opposite direction, so they will repel. Okay, so when the current is being carried in the opposite direction, opposite currents actually repel each other. So same current attract, opposite current repel. Now let us continue with our discussion. Next we will be discussing torque acting on a rectangular current loop. Now torque, basically you can consider this as same as a dipole kept in an external electric field. So in that case the dipole was experiencing a torque, right? So if you keep a electric dipole, so if you remember, we have done this. So if there is an electric field and if you keep a dipole over here, then the dipole experiences a force, right? So we have done this. The expression for torque also is important, and we have done this. Now similarly, in the magnetic field case, we can consider that a current carrying loop is basically behaving like a magnet, right? We have established that a current carrying loop is basically a magnet with behaving like a dipole, small dipole. So when you keep that dipole in an external magnetic field surrounded by external magnets, okay, then there will be a torque acting on this loop. So if current is passing through this loop, then there will be a torque acting on this loop. The expression for this torque is given by tau equals to IA cross B, and in case of n number of turns it is given by tau is equal to NAIB. Okay, torque is equal to scalar form is equal to NAIB. Okay, you can remember it. I generally remembered it as a naib, which is precious, or one student told me in the other day that you can also remember it like Beena, the musical instrument. Okay, so this is also a way to remember it. Whichever way you are comfortable, this torque is given by this formula. This formula is important because you might see one question that a current carrying loop is placed in a magnetic field of this Tesla. What is the torque acting on it? So in that case, you have to use this formula to calculate the torque. Now, the moving coil galvanometer is basically an application of the previous concept, that is torque acting on a current carrying loop. So when a current carrying loop is placed in an external magnetic field, it experiences a torque, and if you apply the same concept and if you fix the loop with a spring, then that current carrying loop is basically behaving as a galvanometer. Okay, so when the torque is acting on it, the galvanometer is trying to rotate, but the spring is trying to stop it. Now based on the amount of current passing through the coil, okay, it rotates at different amount. Okay, more the current, it will rotate more. Okay, so spring has a spring constant, and that spring will try to stop the motion, arrest the motion. Okay, now what is this galvanometer is doing? That galvanometer is measuring whether a current is being passing through this coil or not. So basically the purpose of a galvanometer is to determine whether current is passing or not. Okay, it cannot directly measure the current, or it cannot directly measure the voltage as well. Okay, it is only its only purpose is whether current is passing or not. Wheatstone bridge, if you remember, in Wheatstone bridge the galvanometer was there, it was only detecting the direction, the current, whether it is passing or not. If current is 0, we say that Wheatstone bridge is in balanced condition, right? Now moving coil galvanometer works on the same principle. Now if the galvanometer deflects by an angle, say phi, so suppose normally this is the normal position, and after the current that is being passed through it, the angle of deflection is given by phi. Then okay, if the current passing through this is given by this angle phi, then phi is equals to G into I. Okay, G is the galvanometer constant and I is the current which we are trying to measure. Okay, now the galvanometer constant for a given galvanometer is given by NAB divided by K. N is total number of turns in the galvanometer, A is the area of the galvanometer loop. So if this is a loop, okay, how many loops are there? Total n number of loops are there. Okay, and area of one loop is say A. So this is NA, B is the already existing magnetic field, and K is the spring constant. So including everything, we get the galvanometer constant, which for a given galvanometer this is constant. Now galvanometer's application does not end whether current is being flowing or not. We have to move little bit higher, and we have to exactly able to measure the current. Okay, that's why we need to convert galvanometer to an ammeter. Ammeter is a device which measures current, right? And to measure current, where you have to connect the galvanometer, suppose this is the resistance. So the resistance is carrying some current. Where you connect the ammeter? The ammeter has to be connected in series, so that same current passes through this as well. Because we know in series combination current remains same, so the ammeter has to be connected in series so that it can measure the current. Now ideally an ammeter should have a zero resistance. An ideal ammeter should have a zero resistance, so it does not affect the original current which is passing through it. Right, it should not affect the original current which is passing through the ammeter, right? But if ammeter has a high resistance of its own, then when you put the ammeter in the circuit, the current decreases because overall resistance of the circuit increases. Series combination, resistance gets added. So if the ammeter itself has a higher resistance, then the total resistance of the circuit will increase. right? So what is our aim when converting a galvanometer into ammeter? Galvanometer does not care, okay, it is not measuring the current, it is only saying that okay, current is flowing or not. So galvanometer does not care whether it is able to measure the current or not, but ammeter has to be very cautious that it should not have a very high resistance so that it does not disturb the original condition of the circuit. Okay, so that's why ideal ammeter should have a zero resistance, but it is not possible. So in reality, ammeter should have a very low resistance. So an ideal ammeter should have zero resistance. In practical ammeters, the resistance is kept as low as possible. Okay, to convert a galvanometer into an ammeter, we need to connect a shunt of small value resistance in parallel to the galvanometer. So shunt is basically a small value resistance which is connected in parallel. Okay, any resistance which is connected in parallel is called shunt, and for galvanometer also it is basically shunted. Shunted means what? Shunted means the current, total current in the circuit, say I, only a small portion of the current is being allowed through the galvanometer, because galvanometer also has a limit. It cannot carry a very high amount of current. Okay, by default a galvanometer has say milliammeter or microammeter current it can only allow through it. So the remaining current should pass through the shunt. Okay, the remaining current I minus Ig should pass through the shunt. That's why it is called shunting. Shunting means it is basically taking the extra current and allowing it to pass directly. Okay, and the current sensitivity of the ammeter is given by phi by I, and it is equals to NAB by K. Current sensitivity can be increased by increasing the number of turns in the galvanometer. Okay, then total number of turns that is already there in the galvanometer. If you increase the number of turns, current sensitivity increases. Now the current that we are trying to measure can be calculated using this formula: I equals to Ig G plus S by S. Okay, this is the current that we are measuring. This is the galvanometer current. G is the resistance of the galvanometer. S is the resistance of the shunt. Now this can be useful in numerical questions. Now let's move on to the next application, that is galvanometer to voltmeter. Now voltmeter, unlike ammeter, is connected in parallel because we are trying to measure the voltage, and voltage is constant in parallel combination. So that's why voltmeters are connected in parallel with the resistance. Now when you connect something in parallel, then what happens is that the resistance, if the voltmeter has a very low resistance, then this combination will have a much smaller resistance. Okay, because in parallel combination the combined resistance decreases. Okay, and that's why the ideal voltmeter should have infinite resistance. An ideal voltmeter should have infinite resistance so that it does not affect the original resistance. Right, but in practicality obviously infinite is not possible. So in practical the resistance is kept as high as possible. To convert a galvanometer into a voltmeter, we need to connect a high value resistance in series to the galvanometer. So here is the galvanometer, here is the resistance which is connected in series, and the current flowing through the galvanometer should be restricted to Ig only. Okay, and voltage sensitivity is given by NAB by RK. So if you see that here we have one extra R, and this R is very tricky. Okay, this is the resistance of the coil, and resistance of the coil is dependent on the length of the coil. That means it is dependent on the total number of turns of the coil as well. Okay, that is why N divided by R is actually a fixed value. Number of turns divided by resistance is a fixed value. So even if you increase the number of turns in the coil, okay, the resistance will proportionally increase, and you cannot increase the sensitivity of the galvanometer or the voltmeter, sorry, using the number of turns. So in case of current sensitivity, you can increase the number of turns, and the ammeter should be more sensitive. Small amount of change. So what is the meaning of sensitivity? Sensitivity means it can detect a very small amount of change as well. So even the current changes, say 1 ammeter to 1.1 ammeter, it should able to change. It should able to detect that change and show you a corresponding reading. Okay, voltage sensitivity is slightly tricky. Voltage sensitivity cannot be increased by increasing the number of turns. In this case, only way to either increase area or increase the magnetic field. So voltage sensitivity can't be increased by increasing the number of turns. The voltage that you are measuring is given by Ig into G plus R. Now let's solve one question. That is the last topic, last question of the day. A number of turns in a coil of the galvanometer, not last, we have one more question. The number of turns of a coil of a galvanometer is tripled. Then both voltage and current sensitivity remains constant. Voltage sensitivity increases 3 times and current sensitivity remains constant. Both voltage and current sensitivity decreases by 33%. Voltage sensitivity remains constant and current sensitivity increases 3 times. So as we know that you cannot increase the voltage sensitivity by increasing the number of turns. So only current sensitivity can be increased, and it is so voltage sensitivity should remain constant, current sensitivity should increase by 3 times because you have increased the number of turns to 3 times. Okay, so current sensitivity increases, voltage remains same. Now last question. A galvanometer of resistance 50 ohm is connected to a battery of 3 volt along with the resistance 2950 ohm in series. A full deflection of 30 division is obtained in the galvanometer. In order to reduce this deflection to 20 divisions, the resistance in series should be. So when you are getting the full scale division, what is the current, that you have to find out. Okay, so this 30 division is important, but we will come to that in a while. So when the voltage is 3 volt, the resistance of the battery is 50 ohm, resistance of the galvanometer is 50 ohm and external resistance is 2950. So what is the total resistance of the galvanometer? Total resistance of the galvanometer is R plus G, that is 2950 into plus 50. That is 3000 ohm. Okay. Now when you are connecting this to a 3 volt battery, what is the current? Current is given by obviously the voltage divided by the total resistance, that is 3 volt divided by 3000, that is 1 milliampere or 1 into 10 to the power of minus 3 ampere. Okay, so this much current is being allowed through the galvanometer. Now in order to reduce this deflection by 20 division, so you are reducing the deflection from 30 to 20, then what you have to do, only way to do it is you have to reduce the current. Only way to reduce the deflection is to reduce the current, there is no other way. Okay, how can you reduce the current? By increasing the resistance. Okay, so for 30 divisions, how much current is required? So for 30 division, we require 1 into 10 to the power of minus 3 ampere current. So for 20 division, we require 20 by 30 unitary method into 10 to the power of minus 3 ampere current. So we have to reduce the current to this value. So if this is the current, then current should be equals to this, and what is the value of current? 3 volt battery divided by the galvanometer resistance plus the new resistance, and that is equals to 20 by 30 into 10 to the power of minus 3. Obviously 0 cancels. Now 3 by 50 plus R, galvanometer resistance is 50, and that is equals to 2 by 3 into 10 to the power of minus 3. Now do the cross multiplication, we get 3 3s are 9,000, 10 to the power of minus 3 comes over here and becomes 1000, and that is equals to 100 plus 2R. Okay, so 2R equals to 8900 or R equals to 4450 ohm. Okay, so the resistance is 4450 ohm. So this is the answer for this question. So you have to remember that galvanometer deflection is proportional to current, and to change the current you have to change the resistance, right? Formula sheet of today's lecture. Formula sheet, Lorentz force, Biot-savart's law, force acting on a current carrying wire, everything is compiled, and all the information are over here. So if you want to remember this, or you want to revise this chapter quickly, you can go through the formula sheet and everything will be come to your mind quickly. Next, magnetic field, two parallel currents, current loop carrying current, current carrying state conductor. So everything is again in the same page. And last is torque acting on a rectangular loop, galvanometer to ammeter, galvanometer to voltmeter. Okay, so all formulas at one place, and any required formula you can use it this sheet for. Okay, so all the best for your KCET and PUC preparation. If you have any doubts, don't forget to mention that in the comment section of this video, and I will be back with a new chapter. Also, I will be taking live very soon, so don't miss my live where I will be discussing KCET questions for the past few chapters that I have completed. If you have any doubts, any questions, you can come and ask me in the live session as well. Thank you. See you soon. Till then, bye.